question. What does it say? Yo, Rada, what does it say? I have the same thing. The same thing as me. My canvas isn't working.
Does it work?
Yeah, same thing. It's not working
For you as well?
Yeah.
Do you have the same problem?
How do you fix it?
Comme ça.
It'll fix itself.
Yeah, itself. T'aurais dû se taper. Non. Allez, bien sûr. Bien sûr.
Actually, no, I think I have it. But my pen's not working as well. So
Okay. Good morning. Good morning. How are you? Okay. Fine. Today we are going to finish this topic number 4 about probability. Do you have any question? No. Conditional probability. Dependent event. Okay. This last part is about how to apply probability theory to health science. Okay. This part is boring, maybe. There is no map. Then, when diagnosis in health science is an example of probability theory. Okay. When you go to a doctor. Okay, you diagnosis is an example of the application of probability. Okay, when you go to a doctor and you tell him or tell her your problem, he decides which condition you most likely have. Okay, probability. Okay. To detect a disease or to diagnose a disease, we use tests. Okay, do you remember the PCR, the stick, your nose, the COVID? So to make the diagnosis, we use tests. Okay. And there exist some reference tests. Okay, that are called gold standard. Okay. Ideally, we want the test to be perfect. Okay. A perfect test detects all the positive cases. Okay, all the positive patients that have a condition, that have a disease. Okay. Only if the patient really has the disease. Do you understand? And also a perfect test reject all the cases where you don't have a disease. Okay, this is like the perfect situation. This is not real. Hola. Okay, this is not real. In reality, texts are not perfect. Okay? Maybe you have a person that have a disease, but the test, no, you don't have a disease. Okay? And that's a problem. Okay, so in real life, tests have a certain level of sensitivity and specificity. Do you know the difference between sensitivity and specificity?
One is for sensitivity, it can be wrong, and the other is for specificity, it can be right.
Okay, specificity, sensitivity, and specificity are two measures. Okay, are two important measures in the evaluation of the performance of a test. Okay. The sensitivity is the ability of a test to detect all the positive cases. Okay. You understand? No. Then the sensitivity is the ability to detect all the positive cases. Okay. If you have the disease, then if the test has a high sensitivity, then it detects the disease. Okay. On the other hand, specificity is the ability of a test to identify the people that doesn't have the disease. Okay. You understand the difference? Sensitivity detects all the positive cases, or try to detect all the positive cases, while specificity detects all the negative cases. Okay. Okay, so sensitivity detects the disease. Specificity rule out the disease. Okay, detect the negative cases. You don't have the disease. Okay. That's the main difference. Okay, then if the sensitivity is perfect, okay, the test is perfect in sensitivity, then the probability that the test is positive when you really have the disease is 100%. Okay. On the other hand, if you have a 100% of specificity, then the test is negative when you don't have the condition. You understand? Yes? Easy. Okay, now we have two possibilities. If the result of the test is positive, then we have two possibilities. They are true positive. Okay, a true positive is a patient that has a disease and the test detect the disease. Okay, you are positive in the test and you really have the condition. Okay. This is a true positive. If the result is positive, maybe you are a false positive. Okay, so the test is positive, but you don't have the disease, the condition. Okay, good? This is a false positive. The result is positive, but you are healthy, or you don't have that disease. On the other hand, if the result is negative, then you also have two possibilities. maybe you are true negative, okay? Then the test is negative, and you really don't have the disease, okay? These are true negative. Good. On the other hand, we have the false negative. The test is negative, but you have the disease, you have the condition, okay? Okay, this is important, okay? But I think it's easy. Okay, then a test with 100% sensitivity detects all the cases of the disease. Okay, only when the disease is really present. Okay, so the sensitivity wants to detect all the true positive, okay, and reject all the false negative. Why we want to reject all the false negative?
There'll be someone with a disease, but they don't know they have the disease.
Yes, sensitivity wants to detect all the positive cases when you really have the disease. Okay, if you are a false negative, you have the disease, but the test is telling you that you don't. Okay. Then a test with 100 sensitivity has a few false negatives. On the other hand, a test with 100 specificity proves that in the absence of the disease, the test is always negative. Okay? If you don't have the disease, then the test is negative. Okay? Then 100% specificity means that you have few false positive. False positive is people that is healthy, but the test says that you have the disease. Okay, this is the same. Okay, high sensitivity, few false negative, and many false positive. Okay, how we can obtain the ratio of true positive? So the true positive well, not true positive, but using that kind of things, how can you define the sensitivity without looking your PowerPoint? What is sensitivity? What sensitivity is?
It's to find the positive.
Yes, you want the true positive, okay? You want to maximize the true positive. If you have the disease, then the test should be positive, okay? Then this is the ratio between the true positive and all the people that have the disease. How we can, using this, how we can obtain the total number of people that have the disease?
True negative. Like,
The fake positive plus the
Yes.
yeah.
fake
The
negative.
people that has the condition are the true positive, but also the false negative. You understand why?
Yeah.
True positive, you have the disease, and the test is positive, and false negative, the test is negative, but you really have the disease. Okay? And how about the specificity? Okay, specificity wants to
The true negative.
yes, detect the true negative over the total population that is that don't have the disease. Okay? If you don't have the disease, you can be a true negative, right? Or a false positive. Easy. Then here you have the formulas for the sensitivity and the specificity. Do you understand why it's in this way?
Yes.
Well, here you have the formula. Okay, this is the same, but here the true positive are called A, the fake negative, the false negatives are called C, and the ratios are the same. Okay, just it's matter of notation. But I prefer the other one. Okay, then the idea is to have a 100% sensitivity and 100% specificity, right? Then you detect for the positive cases when you really have the disease, and you detect on the negative cases when you really don't have the condition. Okay, this is the idea, but that's impossible. Okay, to have a 100% specificity and 100% sensitivity. Okay? If your sensitivity is high, then usually the sensitivity is low. Okay? Then for this reason, it's important to know if we prefer to detect the people that have the condition or to detect the people that don't have that condition. Okay? Yes? If you prefer to detect the people that has a condition, you should improve your sensitivity or your specificity. If you want to detect the positive cases, the people that has a condition, you should improve your specificity or your sensitivity.
Sensitivity.
Okay, let's do this example. Okay, then we have to obtain the sensitivity. Okay, using this data, how can we obtain the sensitivity? Yes, true positive over all the people that is positive. You are positive, you are true positive or are false negative. Okay. Then well, using this data, true positive as before, okay, because the proof is positive and you have over plus the false negative. Okay? False negative because you have the disease but your test is negative. Okay? So you have a sensitivity of around 22.5%. What is the meaning of this number? Yes. That the sensitivity is 22.6%. It's not very. The sensitivity is not very high.
The percentage inside the sensitivity is
On the pad.
the occurrence
Yes, the accuracy of what?
of finding the yes positive.
22.6% of the people you analyze are true positive. Really have the disease. Okay? And how about the specificity? Specificity is the ratio between the negative and all the people that don't have the disease.
No, it doesn't work.
If you don't have the disease,
So
you are
she explained
negative
closer so we don't have to.
or a
It's just like atoms of microscope.
or positive because you don't have the disease, but your test is positive. Then 9,000.
It's 99%.
And what these numbers mean? What is the meaning of specificity 0.997? Yes, very specific, but a bit better meaning. I mean, this number, what's the meaning of this number?
That if you test negative, there's a big chance that you are really negative.
What? Sorry? What?
If you test negative, the chance that you are really negative is very high. The accuracy of being negative is very high.
Yes. Then what? The 20?
False positive, right?
Yes.
Why isn't it 160? Why is it 116?
Yes. Yes, because specifically, you measure the true negative over all the population that don't have the disease.
Okay, but isn't that it says that it's
No, because a false negative, if you are a false negative, your test is negative, but you have the disease. Okay, here you have is the true negative, the people that don't have the disease, okay, over all the people that don't have the disease. If you don't have the disease, you can be a true negative or a false
You know
negative.
what it is?
Then this number means that the 99.7% of the people don't have the disease. Okay?
You have to study it. I'm not studying, I'm just going to read it.
Okay? Very well. Then you have the solution. Okay, now we are going to study the disease predictive values. Okay? These values tell us the probability of being sick when the test is positive and the probability of being healthy when the test is negative. You understand? Okay. Come on. Then we define the positive predictive value. The positive predictive value tells us the probability of being sick when the test is positive. Okay. How can you obtain this probability? Using Laplace rule. Similar.
True positive.
Yes. Is
Yeah.
true positive.
Here. And another true positive plus false positive.
Moi, je pense que la chance,
MVP.
And another true positive plus false positive.
Yes, and one. But you have power.
Ça existait.
Okay, yes. It's the ratio between the true positive and all the people whose the test is positive. Okay? Yes or no? Okay, the true positive over all the people for which the test is positive. Okay? This is the positive predictive value. And the negative predictive value,
Same thing with
yes, the negative predictive value is the same.
false negative.
Yes. It's the ratio between the true negative and all the people for which the test is negative. Okay. Easy. Can I continue? Okay, then for the example before, okay, for the example before, the positive predictive value is just the true positive over the true positive plus false positive. You use this data, you get the value. Okay. Is the ratio of the true positive over all the people that is positive. 64. And for the negative predictive value, yes, the true negative over all the people that is negative in the test. Okay. Can I continue?
Vale, Adrián. Pero mi pobre.
Okay. The predictive values give you the probability. Okay. And these values depend on the prevalence of the disease. Okay. These predictive values depend on the prevalence of the disease. Okay. The higher the prevalence, then the positive predictive values increases. Why? If the prevalence is high, then it's more likely that you to be sick, right? And the higher the prevalence, the negative predictive value decreases. Why? Do you know what is the prevalence? The prevalence is that the presence of the disease. Okay. Then the higher the prevalence, the negative predictive value is decreases. Okay, because it's less likely not to be sick. Okay. For example, here you have an example. Okay, this is a table. Here you have the prevalence of a condition, of a disease. Okay, it's an example. Okay, then if the prevalence is higher, okay, then the predictive value is going down, not too much, okay, because it has a good specificity. But the normal situation is that if the prevalence is higher, then the predictive value negative goes down. On the other hand, if the prevalence is higher, then the positive predictive value is higher. Okay, because it's more likely that you may have the condition. Okay. And this is what I explained. Okay. Understand? Yes. Okay, example. Very important. Okay, don't speak too much, but this is very exciting. Okay, here you have a town of 10,000 inhabitants and the prevalence of a disease is 100%. Okay? You have a sensitivity of 98% and a specificity of 99%. Okay? Then, the total population is 10,000, right? Then, how many people have the disease? The number of sick people. Okay, we are 10,000 people.
100.
Yes, why?
1%.
The prevalence is 100%. Okay, then the sick people is 0.01 times the hospital. Okay. And the non-sick people. And remaining.
The rest? Yeah.
Then what is the sensitivity? We want the positive predictive value and the negative predictive value. Okay? You remember the positive predictive value is the true positive over all the people that is positive in the test. Okay. And the negative predictive value are the true negative over all the people that is negative in the test. Okay? Then to solve this exercise, you need the true positive and the false positive, the true negative and false negative. Okay?
Yes.
How can we obtain these numbers? Using the sensitivity.
Sensitivity is for true positive. Find true positive.
Yes, sensitivity is true positive over
True positive plus false positive.
okay. We want to detect all the positive cases. If you are a false negative, you have the condition. This is 98%. Then what this number mean?
Pour les trous positifs et les faux positifs. Ouais, voilà, c'est des signes positifs et les trous positifs. It's true positive plus false negative is the sick people.
Yes.
True positive plus false negative is the sick people. So we can have true positive.
So we
We do
do
0.9 times 100.
Yes, this is okay. If you do this, then you obtain. Yes, if you use this formula, Okay? You multiply both sides, but this sum, okay? And if you make calculation, you obtain that the true positive is 49 times the false negative. And you is yeah, this is okay. This is okay. This is but this number means that 90% of the people are correctly identified as true positives. Then this means that true positives are what number?
98.
It's 98 because it's the 98% of the sick people are correctly identified. You understand? Yeah. Sensitivity want to detect all the sick people, all the really sick people. Then if the sensitivity is 0.98, then the true positive is the 98% of the sick people. Then this is okay. And the false negative 2. False negative
Why wrote true positive equal 49 times
yes. Because if you do this operation, you get this formula. But it holds because true positive is 49 times false negative. 49 times 2.
Where does the 49 place for?
Yes, because you do some algebra, you get true positive 1, 2.
And then you put under
And you operate and this number is 9. Okay? True positive is I don't care about this number. This is perfect. You get this, perfect. Okay, I mean, I don't care about this number and about this calculation. Okay, I only want you to know that if the sensitivity is 0.98%, yes, then the true positive are 0.98 of the total number of sick people. Yes. Then I forgot about it's okay, it's perfect. Then you have that the true positive is 98 and the false negative is 2. Do you understand or should I repeat the operation? It's okay. 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 And what about this? Okay, we have the true positive and the false negative. Okay? We need now the false positive and the true negative. How can we obtain the false positive and the true negative? Using what?
the specificity.
Yes. Okay, now with the specificity, we have that the specificity is the true negative over the true negative plus the false positive. And this is 0.99. Okay? Then, what's the number of true negative? Okay, the specificity is 0.99. Then, what is the number of true negative?
So we know the specificity is 0.99. So we multiply this by the non-sick people.
Yes. Yes. The true negative is specificity times the number of non-sick people. Why? Yes.
Between the people who are
Specificity measure the really non-sick people.
Yes.
Okay? And this number is okay, then this number is okay.
ça c'est les true negative.
This is the true negative. Is the specificity times the number of non-sick people.
Moi je fais un peu d'endroit. Ouais. Non,
And then what is the ratio of false positive?
99.
Why?
But it's the rest
Yes,
of
it's the remaining. You have 9.
of the non-sick people.
Yes.
Putain, le problème est assez déjà.
Ils sont en train d'acheter.
Okay, then the false positive are 99 because if you sum 99 plus this number, you get the total number of non-sick people. Yes. What?
The last thing we did, we did the 908, 9,800 and the 99.
Yes. The specificity is 0.99 because it's a
Yeah.
okay. Then you know that the specificity measure the total number of people that are not sick. Okay? Then the true negative, so the people that are negative in the test and really don't have the disease is the specificity 0.99 multiplied by the total number of non-sick people. Because the 99% of the non-sick people are being correctly identified as negative. Okay? No, the true negative are 0.99 times the total number of persons. And why the false positives are 99? Why? Because they are not sick. The test is positive, but it's false positive because they don't have the disease. Okay. Then what is this value?
The predictive positive value is 98 over
Is that the positive? Yes, right?
I see. You got my shoe.
Okay, then if you want to obtain the PPV and the MPV, then you just replace the positive by the number of the positive. Okay, you replace the number and you get the positive predictive value and the negative predictive value. Okay?
Yes.
Okay, take a photo or whatever you want.
Crazy state.
Little break?
10 minutes. No, but give me now 10 minutes and then Okay. 10 minutes. Here you have another example. Okay? Listen to me. This is another example, but it's the same, but now the prevalence is not 100%, 1 50%. Okay? Try at home. Because it's the same. Okay? Now you have here the solution. Okay? Then try to understand this exercise. Okay? It's the same, but now the prevalence is 50%. Okay? You have the slide, right?
I don't have the same one.
And here you have another example, but another prevalence. Okay, but it's the same. Now, try without. Not now, at home. If you have any question, let me know. Okay, 5 minutes, finish. Here we have another kind of exercise, okay, about this. Let's do this and break. Okay, here you have a table, okay, and the total number of population, the population is 400 patients, okay, and we use the gold standard PCR technique. Okay, looking at this text, you have to obtain the number of true positive, the number of true positive, number of true negative, false negative, and false positive. Okay, what's the number of true positive? Okay, true positive is just a number, it's not a weight.
True positive, 91.
Why?
The people having the COVID and it is positive.
Yes. And the one patient, they detect the antigen, okay? Then they are true positive. They have the virus.
Quand tu veux faire prévalent, moi je fais le calcul prévalent, tu veux quand tu fais comme ça. Quand tu veux faire le calcul, c'est un utility ou
How about the true negative?
True negative? No, 250.
Why?
Because the people who doesn't have COVID are tested negative. False negative 9.
False negative 9, right?
And 15.
Okay, yes. If you add the true positive and the false negative, you obtain the total number of people that have the condition. Okay? Then 100. So,
Il a dit on finit pour 3 minutes.
Next. Okay, now a break.
Ah non, celle-là, tu la touches pas. Parce que je changeais le live pour le projet. Je me mets
Les amis.
Et tu pars où pour le mec qui arrive, il est en retard.
Attendez, il arrive, il est en
Et évidemment,
Vous savez, à chaque fois, je fais ça,
When you go down the stairs, on A, like, there'll be straight ahead, there's like a corridor.
Kimi, est-ce que tu as utilisé pour l'anatomie?
Comment ça s'appelle le truc que je connais? Like, I don't know. Like,
Les minutes, tu connais pas une minute?
ça va. Même, dès que ça passe au-dessous des cheveux, là, ça me dit chaud. Ici. Ah, mais je sais, en fait. Oui, là, elle était là. Non, je suis pas allée à la salle hier. Allez, à niveau de You went? No. Tonight? Really? Because I was studying. Attends, quand je dis que je suis à la maison étudiante, je suis à Hugo. Et c'est un truc. C'est une paix, toi. Plusieurs. Regarde, moi, je suis. Ah, regarde, il y a les amis. Yeah, but like, this one is this one. Like, no,
Ah, je parle de toi, oui.
you know, like the small streets, but like big house, and like there's like lots of little residents, like of 40 people. Like mostly live in Mexican and Spanish people. But yeah. You ready for the anatomy test?
Il y a quoi?
Je peux plus d'air.
C'est autre chose comme la chose de biochimie. Ça, c'est ce là. Oui, on a 7 topics pour passer. Je crois qu'on a fait
Je fais plus beau, il fait plus voir.
mais je dois sortir sinon je vais venir fois.
Ok, viens. Tu viens ce soir? Ouais. De quoi? Mélanie, elle est pas trop forte, mais elle est pas trop. Tout en haut là, c'est ça, c'est qui est utilisé.
La cellule qui a des extensions pour la cellule.
Non, oui, Bumble. Bubule, c'est celui qui en plus qui s'ouvre pour la régénération, c'est ça s'élargit.
C'est un bubble.
Oui, bulbe. Un bubble. Attendez, 8. Germinal, non, c'est pas ça. Ah non, je l'avais vu. Si, Germinal meilleur, si je l'ai vu au pays. Et external meilleur,
Ça, je sais. Réticule.
c'est Germinal. C'est le gars.
C'est dingue.
Il n'y a pas de E, réticule. 1, 2, 3, 4, 5, 6, 7, 7. 3, 4, 5, 6, 7. C'est chaud, hein. Non, je pense que j'aurai la moitié. Il y a dans le passage, je pense qu'on a juste un tu vas m'accorder le chien. Tu vas m'accorder le chien.
Just study for the anatomy test.
Sorry?
The anatomy test.
Yeah.
I know like
Yeah.
not all of it, but some.
Yeah. That's nice.
I read like the chart, like the protocol. Like there's an open test question at the end.
Sorry?
There's a test at the end.
Yeah. I think we do have a test.
Today?
Yeah.
Okay. Let's start topic number 5. Any question about? Any question or not? If not, then come on. We are going to start topic number 5. For me, my opinion, this is the most interesting topic for me. But maybe
The first one is the most difficult.
what?
The first topic.
Yeah, like
Yeah.
state of deviation.
No?
Yeah, I love that.
Yeah, it was Gucci, but this I don't
First
know.
one,
I don't know if it's Gucci.
For me, this is the most interesting, but it's also the most difficult.
I did that.
Oh.
But maybe not. I mean, depends on your
Oh no, I don't hate this.
probability distribution. You know the. Okay. We are going to study the binomial distribution. Do you know the binomial distribution?
See?
Yes.
Yeah.
Interesting. But maybe. And do you know the normal distribution? The Gaussian distribution? The normal distribution?
Is the thing with the how to say it? The curve.
Yes. Curve. Yes.
And then you have to look into
Yes.
the
Easy.
table.
Yes. Yes, the table, the Gaussian distribution.
Yeah.
And also, do you know the student distribution? Or the Fisher distribution? Or the Pearson chi-square distribution? Easy. Not really? Very easy.
Yeah. Really unfortunate.
Okay, we are going to start topic number 5. The most interesting and difficult topic of the course, in my opinion. Maybe not. Okay, we will define, okay, this is topic number 5. A random variable. Do you know what a random variable is? What is a random variable? Okay, a random variable is a variable okay, a random variable I will denote a random variable with capital letters. Okay, for example, the random variable x is a variable, a function that takes elements from the sample space and give us a real number. Okay. This is more very more general, but we can define a random variable in this way. It's a function that takes element of the sample space and give us a real number. Okay, and we assign probabilities for this variable. For example, the probability that the random variable is, I don't know, equal to. Okay. Then we assign probabilities to this variable. Okay. Probability, nothing new. We use the tools that we have here. Okay. Then with these tools, with this random variable, we assign probabilities to characteristics. Okay, for example, blood pressure. What is the probability that your blood pressure is between 100 and 120 millimeters of mercury? Okay. We assign probabilities to a random variable. Random variables can be what? Discrete? Or continuous. As always, okay? Discrete, if we have a finite number of values or a finite number, but with one by one correspondent with the reality. Okay, do you remember that things?
Yes.
And continuous values, random variables can take any value in a range. Okay, for example, the temperature, the temperature, or whatever. Okay. Then, if we measure a random variable in a population, is the same. Is like if we obtain the frequency distribution. Do you remember the frequency distribution, the table with the absolute frequency? Yeah. If you don't have the frequency distribution, maybe we have the chord, okay, the Gaussian chord, the probability distribution. Okay, this is called the probability distribution. How the probability is distributed along the population. Okay, if you know this chord, we can do theoretical calculation of probabilities. Okay. For example, consider this experiment. Okay, we flip a coin 3 times. Okay, what the sample space is in this experiment? If you flip a coin 3 times, what are the results that you can take? Yes, essentially, yes, and you can take 3 heads, head, tail, head, tail, tail. Head, take head. Tail, take head. Tail, head, tail. Head, tail, tail. Tail, tail, tail. Yes, that was what we want. Yes. Okay, you flip a coin, then you can obtain all these possibilities. Now I will define the random variable x. Okay, if I define my random variable to be the number of heads, in this experiment. Okay. Then x then the random variable here is the number of heads. Okay? Then we have 3 heads. Then what is this random variable if I obtain 3 heads? X is the number of heads. Then if I obtain 3 heads, what will be this number? 3. Now I can obtain 2 heads. And then this number is 2, right? For all these possibilities, for all these events, we have 2 phases, 2 heads. Okay, you understand? We can also have this configuration. we only have one head. For all these three possibilities, we only have one head, okay? And the last one is 3 tails, okay? Then this will be 0 because we don't have heads. Good. Then now I'm asking you. I will clean. What's the probability of obtaining 0 heads? Okay, what's the probability that my random variable x takes the value 0? What's that probability?
A what?
108.
Yes, 108. You only have one choice, 3 days, over the complete sample space, okay? Okay, if you don't want this form, okay, you don't want to count about the possibilities, to head, tail, head, you know, then what is this probability? This probability is also the probability of tail, intersection tail, right? Tail and tail and tail. Yes? The same. 0 heads or 3 tails. The same. Here you have a probability of an intersection. What is the probability of the intersection? Are they independent or dependent events?
Independent.
Independent. Then the probability of the intersection is, if the events are independent, we saw it yesterday. If the events are independent,
What do you mean?
yes, the product. Probability of tail. Okay. Which is one over 8. It's the same, okay? Here we have used the Laplace rule, okay? The favorable cases over all the possible cases. And here we have used the probability of the intersection, okay? But it's the same. Okay? Then what's the probability of getting one tail? Sorry, one head. One head. What is the probability that my random variable is equal to 1? Yes, you're right. Okay? Because you have 3 possibilities. These 3 possibilities over 8. If you don't like Laplace rule, you can apply the probability of 2 intersection. Okay? This is 3 times, because you have 3 possibilities, the probability of getting one head and 2 tails. Yes. The probability is the same. If you get tail head tail is the same probability as tail tail head. Okay, then 3 times the probability of one of these events. Okay, then 1.5, 1 over 2, 1 over 2, 1 over 2 is 1 over 8 times 3, 3 over 8. Okay, it's the same. And the probability of getting 2 heads and finally, the probability of getting 3 heads 1 over 8. Okay, then we have assigned probabilities. Okay, now we have assigned probabilities to an event that is the number of heads. Okay. Okay. Good. Then, using this experiment, we have obtained the distribution, the probability distribution. Okay? Can I? Do you want to take a photo? Okay. Then, what is the probability distribution? We have obtained that the probability of getting 0 heads is 1 over 8. One head, 3 over 8. Then the probability that my random variable takes the value 0 is 1 over 8. Okay? Okay. Or 0. Or 1 is 3 over 8. Do you understand this graph? Okay, this is the probability distribution for our experiment. Okay? This is the probability distribution of a discrete variable. Okay, we have a discrete head or tail. I mean, it's discrete, right? Discrete or continuous? Why?
Because you can have in between.
Then the probability distribution is something like this. If my variable is continuous, then we should have something like that. Okay. Because can take values between 1 and 2, for example. Okay. These all values are well defined here. Okay. Okay. question? No? I can continue, right? Okay, this is what I explained you now. What do you prefer? That I explain in the screen, writing the calculation, or just commenting, talking about the slide?
Right.
What? Right. This is what I have to tell you. Okay? 3 faces, 2 faces, 1 face, 3 heads, 2 heads, 1 head, 0 head. Okay? And the probability of each layer. Usually for discrete variable, the data and the probabilities are calculated, okay, at given interest. But this is the same as I told you now. And here we have the probability. Number 0 corresponds to a probability of 1 over 8. 1 head corresponds to a probability of 3 over 8. Okay, this is what I explained. Okay, in this graph, the root order doesn't make sense, okay, because it's a discrete variable. Just an example. Okay, let's do this example, and that's all. Okay, come on, let's do this exercise. Okay, here we have the probability of rain. Okay, probability of rain 0.4. Then the probability of no rain is 0.6. Is 1 minus the probability of raining 0.6. Okay? They are asking us the probability that rain on 0, 1, 2, or 3 days. Okay? Then, what will be our random variable, our x? Days. Raining days. Okay, then our sample space will be something like that. Rain, rain, rain. Rain, sunny, rain, and so on. Okay? It's the same as before. We have 8 elements because we have 2 possibilities. Okay? And 3. Okay. Then, what's the probability that don't rain in all of these days? Of getting 0 days of rain. Okay. Okay. You say the black room. Sunny, 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 over the 8 possibilities, right? 1 over 8. Then, but if you do this, is the same as this. Okay? Sunny, intersection sunny, intersection sunny. Okay? They are independent. Then you can multiply probabilities. Okay? Then the probability of a sunny day is 0.6. Then this is 0.6 to the third to which is 0.216. Now, do this with the calculator, please.
Zero point 125.
What?
0.125.
125? Okay, then what's the correct answer? This is the correct one. Why this is not correct? 1/8 is not correct in this example. Why? This is the correct one. This is not correct. Why? Because here we have applied the same as before, Laplace rule, 1/8. Why in the previous example these words are now done? Yes, they are independent. But why in the previous example the Laplace rule work and in this example it where can we apply the Laplace rule? Because I told you you can use Laplace rule when you work with a finite sample space, but you have finite sample space. But Laplace rule only works when the probabilities are equal. Okay? In the previous example, the probability of getting a test or a tail was the same. Now, okay, now they are different. Then we can apply Laplace.
Because
Because the probability of the two events are not the same. The probability of raining is 0.4 and the probability of not rain is 0.6. Okay?
Wait, sir, why did you cube it? 0.6 cubed, why?
Because the independent, the events are independent. Okay? If one day is sunny, it doesn't affect to the next day. Okay?
Okay.
Then the probability of the intersection of independent events are the product of the multiplication of the probabilities. Then this is probability of sunny, probability of sunny, probability of sunny.
Okay, so if it was 4 days, you would do it by 4. If it was 4.
Yes, but the change of rain on each of the 3 days.
Okay.
3 days. Okay. Then the probability there are 3. Okay.
Okay, thank you, sir.
You understand why you cannot use Laplace rule?
Yeah, because it's not equal, the probability.
Yes, probabilities are not equal.
if there's 3 events but 2 are the same, we apply the Laplace rule.
No, because probabilities are not the same.
But if 2 of them are the same, and we only want to see like the both.
No, you can multiply the probability of one event by 2. There are 2 various events. Okay? Then this is the probability of no rain. Okay, how about the probability of one rainy day? What is the probability that by a random variable, which is the number of rainy days,
1/8.
why 1/8?
For one rainy day, 1/8. Yes, forgot about the Laplace rule.
It's 0.6 multiplied by 0.6 multiplied by 0.4.
Yes, this is. You can obtain rain, for example, the probability, this probability is the same as rain, sunny, and sunny, right? But this is the same as sunny rainy, sunny, or sunny, sunny, rain.
Okay.
Okay, then it's 3 times this probability. But what this probability is? Yes, this is
0.6.
right? Okay. Okay. Okay, the probability of today with rain. Okay, the probability of today's of rain.
Uh, 0.4 squared times 0.6 times 2. Yeah. Times 2.
This is the same as the probability of, for example, rain, sun. Right? But it's the same as rain, sunny, rain, or rain, sunny.
So how comes in the bottom one you didn't times by 3? You know on the bottom one, px equals 0. You know. But why did oh, okay. So why do you times by 3? When do you times by 3? You know how you put 3p? Yeah, when do you do that? Like.
Yes, because the probability of having 1 day of rain is rain, sunny.
Okay.
But also sunny, rain, sunny. But also sunny, rain.
Oh,
The probabilities
okay.
are the same. Then I multiply by 3 because
Okay.
you have 3 possibilities
Okay.
of 1 day of rain. Okay? And this is the same. You have 3 possibilities.
Yeah, it
of,
can be sunny, rain, sunny,
Yeah.
like that.
yes, rain, sunny, sunny, rain, or sunny, rain. 3 possibilities. Then this is 3 multiplied by 0.4 squared, 0.6. And what about the probability of the 3 days rain?
Yeah. 0.4 cubed.
Yes. 0.4 times 0.4 times. Okay? Then we have assigned probabilities to an event whose sample space is not numeric. It's rain, sunny, rain. But we have assigned probabilities to this sample space. Okay? Which is not numeric. Okay, can I continue? Just one thing. Okay. Go. Okay, you have here, and here you have the solid inclusion.